Hi, I'm Antonio Sala, and in this video we are going to solve an example in Matlab using YALMIP and SeDuMi toolboxes on how to find the ellipse of largest area given a convex shape intersection of half-planes, polygons, and ellipses in which the target ellipse must be. We are using linear matrix inequalities, semidefinite programming, and of course, as it is convex optimization, even if we are doing it in 2D, so that we can easily plot and visually interpret what we are getting, it is computationally efficient, so we can quickly solve the same problem in, let's say, an 11-dimensional setup. So let's go with the details. First, we will need to add toolboxes to the path. And in my case, I used TBX Manager, so I need to do this. But okay, if you installed it from different sources, your Matlab path commands might be different. And on top, you have the versions I used. Well, so let us define the region in which we wish to fit our ellipse. And the region will be that cyan thing, intersection of a polygon and an ellipse. And let us see the final result to motivate. We wish to find the red ellipse, which is the ellipse with largest area inside that region we have here in dark blue. So how do we do it? Well, let us first encode the blue region as follows. An ellipsoid with center C1 and shape matrix Q1 is this equation, and I will encode C1 and Q1, just, I invented it. Then a polyhedron is a set given by the intersection of half planes, each of the half planes given by each of the rows of these linear inequalities. So I have a polygon with 4 sides in this 2D case, faces in a generic setting, so my 4 faces or facets polygon will be defined by, well, some linear inequalities that I just invented. So with suitable f implicit commands, I'll show them in a minute, we are able to plot this region whose frontier is in cyan color, and the region is the intersection of the blue ellipse and the quadrilateral polygon defined by the red, yellow, green, and purple edges. In order to plot this, I will define this ellipfun so that it is positive when x1, x2 are the abscissa and ordinate coordinates of a point, then it's positive when the point is inside the ellipsoid. And these 4 polyfun things are written also so that they are positive if the point with coordinates x1, x2 is at the correct side of the edge, is inside the half plane whose intersection forms the polygon. And then the edge of the set will be drawn by plotting when this set fun is 0, because, well, okay, if I take the minimum of those ellipfun and the 4 polyfun, then if the minimum is above 0, means that all constraints hold and we are inside the requested shape, and if the minimum is below 0, that means that one of the constraints does not hold and we are outside. So set fun being positive is the convex region we wish. And, well, with those f implicit, the ellipse, polyhedra, and set fun, and suitable hold, grid, axis, whatever, we get this representation of our problem setup. So now we need to compute the largest ellipse in the term of largest area inside the cyan region. And how do we do it? Well, we'll use linear matrix inequalities as follows. Our target ellipse will be in this form. The Euclidean norm of some h minus 1 x minus c less than 1. X will be a generic point in the ellipse, and H will be the shape matrix and C will be the center, and both H and C will be decision variables in our optimization problem because we must find the center and the shape of that target largest ellipse. Of course, this is the equivalent quadratic notation defining my ellipsoid, so that the shape matrix I named Q a few lines above here, when I defined my ellipsoid, well, then that Q here will be sort of H squared, because we will assume that H will be also a symmetric positive definite matrix, because from eigenvalue and eigenvector computations with the square root of the eigenvalues, I can compute a symmetric square root of any matrix, so we are not losing generality in saying that H must be symmetric and positive definite, because, okay, we want the positive square root. Let's say 9 has two square roots, plus 3 and minus 3, and we wish plus 3. So, if you believe that we are not losing generality, then let us pose the conditions for this ellipsoid being inside the strange shape we defined a couple of minutes ago. We will define the center of the ellipse, Cx, Cy, as semi-definite programming decision variables, SDP var. We will need also a scalar, sort of Lagrange or Karush-Kuhn-Tucker multiplier, to be also a decision variable. So this is the ellipse center, and the shape matrix will be a symmetric matrix, 2 times 2, and I wish the positive square root, so my first LMI will be H, being positive semi-definite at least. Then we'll start with our first non-trivial, let's say this is an LMI, but okay, it's just because we wish the positive square root. So the first non-trivial LMI we are considering is that my target ellipsoid needs to be inside the blue ellipse here. Of course, I need many constraints, extra ones for the polyhedron, but the first one is that the thing I search must be inside the blue ellipse, and then in order to express that as a linear matrix inequality, I will use the seminal book by Stephen Boyd from Stanford. You have the link here, and in that book, in section 373, it does some theoretical developments that are outside my goal here for brevity, so that it says that my target ellipsoid calligraphic E0 is contained in other ellipsoids which are predefined if this linear matrix inequality holds, in which this is decision variable and this is decision variable, shape matrix and center of the short ellipse, and Pi, Xi are the shape matrices and center of the given ellipses, and this is the Lagrange multiplier, let's say lambda. Then I used another notation in the sense that I called this H, and the center I called it C, and the center of the given ellipse was C1, and this thing I called it Q. But with this change of notation, this is exactly what I did write in the Matlab code at the bottom of the screen. So this is ellipse inside ellipse, and now my second set of LMIs will be those for ellipse inside polygon or ellipsoid inside polyhedron in a generic case, and then I use the LMIs in this PDF from University of Texas. So I need to put an LMI for each phase, and if we see that source, this is the section of the materials you can readily download yourself. And its definition, this is the center, this is the shape matrix, and Y is something in the unit sphere, so that the shape matrix converts the sphere in an ellipse, and D is the displacement from the origin. But okay, this is how they do it, but in my case I call the center lowercase c, and the shape matrix I call it capital H, but we are doing the same. So at the end, the theoretical explanation is in these lines in here that you can, download or pause and inspect by yourself. We are omitting explanation for brevity. The thing is that we end up saying that the required linear matrix inequality is this one, for my target ellipse being inside the polygon. So I did program that in Matlab as follows. Here we have it, but D is C in my code and capital C is capital H in my code. And also I sort of switched rows and columns so that the identity matrix they have here, in my case it is here. So instead of being in the top left block, in my case I wrote it in the bottom right row, but okay, swapping rows and columns and transposing things, we are doing exactly the same conditions. So these are the 4 LMIs needed for ellipse inside polygon. Then this is it. The only remaining thing is optimizing, and then the logarithm of the determinant is the thing that must be optimized to obtain the maximum volume. But okay, it's equivalent to maximizing the geometric mean of the eigenvalues of the shape matrix H. The determinant is the product of the eigenvalues and the logarithm is monotonic. So in the seminal textbook references, they say that to maximize the log determinant, maximize the product of the eigenvalues, and YALMIP has code to maximize the square root of the product of the eigenvalues. So we are doing the same thing, just with, different notation, different gradient computations, but we are doing the same thing. So we call the optimizer that by default minimizes, so we need this minus sign here to maximize the volume. And then this is it. Once we call this, we get successfully solved, good, and we get the values for the shape matrix and for the ellipsoid center. So this was the equation of the short ellipsoid, and here I have it in Matlab code, which is, writing the thing I had here in pretty equation form. And then with the F implicit command, I will draw the edge. So we get what we were seeking, the largest area ellipsoid in this blue convex shape. So with this, we finish our presentation, but okay, if instead of the maximum area ellipsoid, we wish to obtain, let's say, the largest circle, then, for instance, I just would need to change H to be diagonal, let's say, in the sense that, okay, if I comment this, and I say that I need a decision variable which is the radius of the short circle, and H is the radius times the identity matrix, then with this particular shape matrix that represents circles, if I execute exactly the same code, the maximum area circle, of course the maximum radius circle, will have a radius of 1.6, and this is the largest circle that can fit inside my region. So, going back to our original problem, we will summarize what we did. In this video, we found the largest area ellipse, or the largest circle with trivial changes, that fits inside the convex shape given by the intersection of ellipses and half planes, polygons. We can generalize this to higher dimensions, to any arbitrary number of ellipses, arbitrary number of half planes, whatever, and as is this convex optimization, it is efficiently solved. So this is an example of the power of semi-definite programming linear matrix inequalities in some geometric problems involving quadratic forms and convex shapes. So we finish with this. Thanks for watching.